Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with the 11th chapter of microwave engineering where we have the microwave resonators to be addressed for the various microwave applications. As we come to see that the microwave resonators are working for the applications as like the filtering or the oscillations to produce or into also the frequency measurement into the microwave test bench also. We come to have the knowledge that if the RLC, the lumped elements, when are connected into the series and the parallel connections, they are working as resonators. So therefore, we have analyzed first of all in this chapter the series resonant circuitries and the parallel resonant circuitries with the help of these lumped elements there. Next to that, we have also added to the information regarding the quality factor measurement when these RLC circuits for series and parallel connections connected to the load resistance RL. So now we have the knowledge of the unloaded quality factor, the external quality factor, and the loaded type of the quality factor also here. In the previous video that we have seen, a section of microwave transmission line with the length lambda by 2, when it is short circuited at the end, it can also produce the resonance effect when it is of the similar to that of the series RLC resonant circuitry. So let us have the length to be half of that one that we have here, the short circuited condition for lambda by 4. So let us see the details. So here we start with our topic short circuited lambda by 4 line. So as we have the transmission line section, in general I can show these are the two lines. So let us see from this node to this node a pair here. We extend up to these 2 points where as per the title we have short circuiting made here. Now if we have the line length L is equal to lambda by 2 in the previous case, and if we are having the computation of the input impedance Z in corresponding to the characteristic impedance knowledge, the attenuation constant and the phase shift constant, both accounting for the propagation constant. So here in this diagram we have the line length if we have lambda by 2 as the previous case here, with the knowledge of the Z in computed Z0 and alpha with the beta here, such the half wavelength transmission line when short circuited at the end point, so it will be working as the RLC series resonant circuit here. But when we get this length to be more half, so we have L is equal to lambda by 4 instead of lambda by 2. So that time we come to have the performance of such a transmission line where L is equal to lambda by 4. It is short circuited here. It will be working as parallel connection of the RLC components, working as the resonant circuit here, or the resonance condition we can say. Now as discussed into the second topic of this chapter, for the parallel connection of the RLC lumped elements to produce the resonance, this is also said to be the anti-resonance, just to make a differentiation with that of the series performance and that of the parallel performance here. Now when we have the input impedance marked onto the schematic diagram for the corresponding transmission line, we can make its mathematical computation from the formulation, that is using the characteristic impedance Z0 in multiplication to the hyperbolic tangential function over alpha plus J times beta into the line length L here. So here alpha plus J beta, the bracket is in place of gamma is equal to alpha plus J times beta here. We can further express the input impedance Zin with Z0 in multiplication to the hyperbolic tan function over alpha L added to J times tangential trigonometric function over beta L here. So this is divided by, we have 1 plus J times tangential of beta L into tangential hyperbolic function over alpha L. We can also express the input impedance Zin into the form where we have characteristic impedance multiplied to the ratio where we have the numerator 1 minus j times tangential hyperbolic function over alpha n in multiplication to the cot function, the inverse of the tan function, the trigonometric one, over beta into L here. Whereas the denominator is the tangential hyperbolic over alpha L minus, we have the imaginary portion j times cot function over beta into L here. So this form of the equation for the input impedance Z suffix in can be represented by equation number 1 here. So for this generalized expression that we have for input impedance, when we in addition assume that L is equal to lambda by 4, the length of the transmission line, provided that the operative frequency omega is represented by the resonant frequency omega 0, along with letting this omega to be omega 0 plus a small section of variation that it is delta omega. So with this, if we consider the transverse electromagnetic, that it is the ideal mode of propagation here, the propagation information can be expressed into the form beta into L. For the length of the transmission line, it is equal to omega 0 L divided by the phase velocity Vp. It is added to the section of delta omega into L divided by again the same denominator Vp here, which further can be expressed to the form, we have pi by 2 for the first component, and next to that we have pi into delta omega divided by twice of omega 0 for the second term of the RHS here. So using this form of the beta into L, beta being the phase shift constant, L being the length of the transmission line, the trigonometric function cot of beta suffix L can be represented by cot of, inside the bracket we use from the above equation, that it is pi by 2, the first term, added to, we have pi into delta omega divided by twice omega 0 here. So this can also be expressed to the form as it has been added to the pi by 2, that it means 90 degree plus, we have it minus of tangential function over pi into delta omega divided by twice of omega 0, the resonant frequency, which can be further approximated to minus of pi into delta omega divided by twice omega 0 here. Now also, as before, we have done the approximation of the hyperbolic tangential function over alpha into L to be simply alpha L. We consider a small kind of loss here, that it means it is low loss transmission line. So for a low loss transmission line, the equation number 1 that we have approximated for the input impedance can be given of the form Z suffix in is equal to capital Z0, the characteristic impedance, in multiplication to the ratio where we have the numerator 1 plus j times alpha L into pi into, we have delta omega divided by twice omega 0, whereas the denominator is the attenuation constant alpha into the length of the transmission line added to j times pi into delta omega divided by twice omega 0, the resonant frequency. Further, the approximation can be of the simplified form Z0 into the numerator divided by alpha L added plus J times pi into delta omega divided by twice resonant frequency in angular form omega 0 here. So let this can be the equation number 2. So in this equation we have the considerations alpha into L into pi into delta omega divided by twice omega 0 to be very less than that of the 1 here. So when we have a look onto the equation number 2 that has represented the input impedance Z in, so we come to find the similarity with respect to the equation that we have learned before in the same chapter, that it was 1 divided by 1 by r added to twice of j times delta omega into c here. So this is the equation for the second topic. We have obtained the parallel resonant circuitry with the parallel connection of RLC, the lumped elements here. Hence I can say that a section of transmission line which is shorted at the end and having the length of lambda by 4 is working as the parallel resonant circuitry. So for such a transmission line that is having the effect of parallel RLC component resonant circuitry, we can find the equivalent components for R, L and C. For the resistive part, the representation of R can be in terms of the characteristic impedance Z0 divided by the attenuation constant alpha into the length of the transmission line. So this is the important case which is accounting the power losses that we can further express in the terms of the quality factor. Whereas the other two components that are responsible for the storage of the magnetic and the electric components are, so for the electric storage form of the energy, we have the representation of capital C. The capacitance value is obtained into the equivalent form given by pi divided by 4 times the angular frequency at resonance condition omega 0 into the characteristic impedance Z0. So this is the second equivalent component. Whereas the component that is responsible for the storage of magnetic form of the energy for the resonance condition, we obtain the inductance L is equal to 1 upon the square of resonance frequency omega 0 into, we have here the capacitance C here. So let us outline all these three components that are the parts of the equivalent circuitries there. At the last, we express the unloaded type of the quality factor, that is by Q suffix 0. So as we have the performance of short circuited lambda by 4 transmission line as that of the parallel RLC resonant circuit, we have the unloaded quality factor Q0 expressed in the form of resonant frequency omega 0 in multiplication to the equivalent components R into C here. It can also be further expressed in the form of pi divided by 4 times alpha into L, which is equal to the phase shift constant beta divided by twice of the attenuation constant alpha here. So here we have the substitution of small l is equal to pi divided by twice beta to produce this relationship here. So here, as we see here, that the quality factor Q0 is having inverse relation to that of the alpha. So with increase into the attenuation constant, there it will be the reduction into the quality factor. On the another hand, if you want to have the quality factor at unloaded condition to be increased, we should have decrease into the attenuation constant there. So here we conclude our topic short circuited lambda by 4 line, which is working as the parallel resonant circuitry used by the RLC component here for the resonance effect there. So by the next lecture we shall continue our discussion to have the resonance effect with the help of a section of microwave transmission line. So for a generalized case, we shall limit it to the length lambda by 2, but this time terminating it with the open circuited condition. So the next topic will be open circuited lambda by 2 transmission line. So I hope the concepts that we discuss and the knowledge we share for microwave engineering topics is definitely getting you benefited. For more such information and the knowledge, you can subscribe to Ekeeda channel. Thank you.